Hello class. So we are still on Ed Extension program powered by Exponential Computers. Physics lesson 4 prepared by Aliu Lal. Our topic today is this is our outline. This is a topic that we are focusing on today. Application and the interpretation of motion in problems. So our today's topic is uniformly accelerated motion. A question of uniformly accelerated motion. So when we say a question of uniformly accelerated motion, it's a topic that concern with motion. So let us see. A question of motion. When we say a question of motion, we are referring to motion. Motion is the state of changing position of an object over a time. We say motion is a state of changing position. Any changing position is what we call motion. When you change position from one place to another, you are in a motion. But that motion, you cover a distance, and a distance it measured by a time. The time that you cover from one place to another is what we call we are in a motion. So motion is a state of changing position of an object over a time. You can change a position from one place to another. Maybe you can change position from one place to another within 2 minutes or 1 second. It measured by time. This is what we call motion. It's a rate of changing position. So as you can see, this is the drawing. So this is a motion of these bicycles. This is the racers. This is a motion. This one is they are in motion. Maybe let's say this is number 1, 2, 3, and this is the rest. This one they are in motion. All of them are in motion, are not in a starting point. They are moving from one place to another. They are in rest. They move from one place to another. They need to reach somewhere to be finalized. So this is what we call motion class. Uniform acceleration. So when we say uniform acceleration motion, it's in which acceleration of a particle throughout a motion is uniform. So it's an acceleration of a particle or of an object that be uniform. Any acceleration or so when we say uniform acceleration, it's acceleration of an object that are uniformly, the acceleration that goes uniformly. Examples, let us see. This is the cars in a race, but all the cars are having the same engine, but the color are different, but it has the same engine. Why? Because it is a race. They are uniform. They are uniformly. They are in a race, and they follow one direction. So this is what we call uniform accelerated motion. This is the cars that are race. They are in race, but the cars they have the same engine, but different color. They are in uniform. So this is the equation of motion used to derive the component like displacement, initial velocity, final velocity, change in velocity, initial velocity, final velocity, and change in velocity, then time taken. We are using a equation of motion in order to derive the displacement, the initial velocity, final velocity, change in time, and time taken. This is what we are using a equation of motion for these accelerations. As you can see, this is the acceleration, change in velocity all over time. Anywhere you see acceleration is a change in time all over time. As you can see, the mathematical expression, a is equals to v, which is initial velocity, minus u, which is final velocity, all over time taken. Time taken before from initial velocity to final velocity all over the time that covers. This is what we call acceleration. Then this is a 3 equation of motions that we have. Generally in physics, this is what we call formula for equation of motion. This is our formula 1, which is V. This is our V, which is final velocity is equal to initial velocity plus acceleration times time, our first formula. Our second formula, this is displacement or distance, which is equals to U as initial velocity plus T as time taken plus 1 over 2, which is a half AT square. Our A is our acceleration and the T square is our time taken. This is B square final velocity is equals to U square plus 2AS. This S is representing as displacement or distance. This A acceleration. So examples. Let us take one examples so that we can calculate all using using our formula of accelerate or using our formulas of we can calculate using 3 equation of motion that we have. So as you can see, a train travel at 20 meters per second undergoes a uniform retardation of 2 meters per second square when brakes are offline. So this is a train that moves at 20 meters per second, which is our initial velocity, undergoes uniform retardation. So our acceleration will be retardate, will be decreased at 2 meters per each second square. So when a brake are offline, 1, we said calculate the time taken to cover the rest. 2, calculate the distance traveled from the place where the brake are offline. 3, calculate the final velocity of a train. So if you could remember class, we say we have 3 equation of motion that we have. So we are using each formula to calculate our examples that we have given. So this is our first solution that say calculate the time taken to come to rest. So this is our formula. This is our data. As you can see, solution 1, this is our data. We have initial velocity as 20 meters per second. Then our final velocity is 0. Then acceleration. But remember, the acceleration are in retardation. So our acceleration will be in negative. So we have minus 2 meters per second square. So using our first formula, that say V is equals to U plus a half plus AT. Sorry. So this is our formula. We can insert our values, which is 0 as our final velocity at 0. So class, this is the formula that we are using to calculate our time. So as we can see, we can insert our values. This is our 20. This U represent 20. This 20, if we could remember from our data, this 20 is our initial velocity. So we can represent it as U here minus this minus, as I have told you earlier, our acceleration are in retardation. So we have to minus our velocity, our acceleration. So this is our minus 2 times T, which is our T is unknown. We are looking for T, the time taken. So we can just cross multiply. If we cross this minus 2T, if we take it into the right hand side, it becomes plus 2t, which is equals to 20. Then we can divide both sides by our 2. If we divide both sides our 2, then 2 will go with 2. It will remain only t. This is our t, which is equals to 20 all over 2. These 2 that we are dividing both sides. So our time taken is 10 seconds. This is our first equation using first formula of motion. So second solution, our second solution, it says we are to calculate a distance. So we can use our second formula to calculate the distance. So as you can see, this is a formula that we are using. S, which is distance, equals to distance or displacement equals to initial velocity times time plus a half at squared. So we having our value. What we are looking for is just a distance. So we can just insert our value and calculate our distance. This is the data. This u is our initial velocity. This t, this is the time taken that we just calculate earlier. And this a acceleration, our acceleration is in retardation. It will be minus 2 meter per second square. Then s as a distance is equals to ut plus a half at square. So this is what we are calculating. We are looking for d, for s, which is our distance. So we insert our values as you can see. Our s is equals to 200. This 20 times 10. If you press your calculator, you can see. Then you can say 10 square. This is the value that they are giving us. We have 200. That 20 that we times it by 10. This is our 200. You can, if you press your calculator, you can see. And 10 square, it will give us 100. So this is it. 200, 2 times so 100 will give us 200. Then times our half. So our half is the same thing as our value, our exact value divided by 2. So this is what will represent our half. So our distance is 100 meter. So class, we calculate our meter as 100 meters. This is the meter that train covers. Then solution 3. The solution 3, we are to find our final velocity in a train. Then our data, so we calculate our distance, which is 100 meter, our acceleration, which is 2 meter per second square, then our initial velocity as 20 meter per second, then final velocity. So we are looking for final velocity. Final velocity is not given. So let us see how can we calculate final velocity. Then we can use our third formula. Our third formula that say v square is equals to u square plus 2as, which is our final velocity square is equals to initial velocity square plus 2 acceleration square and distance square. And distance normally there doesn't have square, so we can just insert our values. So class, this is a formula that we are using for calculating for finding our final velocity. As you can see, we're having our data. This is our initial velocity. This is our displacement or distance, and this is our acceleration. So we can just insert our values and start times in it. 2 squared, it will give us 400, and 2 times 100, it will give us 400 still. So our v square is equals to 100. When we add 400 plus 400, it will give us 800. So we are to root both sides. Why? Because what we are looking for is v, not v square. So we are to root both sides to remove our square so that we can find our final velocity. So as you can see, we are root both sides. This root goes with square, and our 800, root of 800, you can press your calculator, class. Root of 800, it will give us 28.3 meter per second. So this is the end of our class. Thank you for listening. See you next time.